In this video, I'm going to go over the Biochemistry Unit Exam 1, Amino Acids and Proteins. So let's get started, where the first part of this video is going to go over the general chemistry and organic chemistry review, where we are going to go over the concepts of electronegativity, the octet rule, intramolecular forces versus intermolecular forces, the hybridization of atoms and their geometric shapes of molecules and the importance of resonance in biochemistry, organic functional groups and resonance and their importance in structure and function. And we are also going to go over pairs of reactions like oxidation reduction reactions, redox reactions, phosphorylation dephosphorylation reactions, acid-base reactions like protonation deprotonation reactions, condensation reactions where we combine two molecules together and release water, hydration reactions where we add water, dehydration reactions where we remove water, and the lipid phases, right? Like what is needed to be on the internal side versus the external side of membranes for ions to pass through. So the next section is going to talk about amino acids, where we talk about the physical chemical properties and the general structure of amino acids. We're also going to talk about the isoelectric pH, aka the pI of amino acids. And we are also going to talk about the classification of amino acids, whether they are ketogenic, glucogenic, essential, non-essential, conditionally essential, and their properties like polar, non-polar, charged, uncharged, positively, negatively charged, polar, uncharged, and some facts to know about them, and some special products that are coming from amino acid precursors, right? And then we are also going to talk about Ka, pKa, and the pH relationships, and buffers such as the carbonate bicarbonate buffer in the bloodstream, right? So let's get started with the electronegativity concept. So think of electronegativity as an affinity to pull in electrons, to attract electrons, right? Where if an atom has more electronegativity, it has a stronger pull of electrons. And let's say this is the periodic table right here. The electronegativity trend is going to increase from down to up and from left to right. You could also think of this as the electronegativity is going to increase in this direction here, right? Where the top rightmost corner of the periodic table is going to be the most electronegative atom, right? And the three most electronegative atoms that we are going to be worried about here is fluorine, oxygen, and nitrogen, right? Everything else is going to be negligible, like carbon, hydrogen, every other atom is going to be less electronegative than these atoms here, right? These atoms have more electronegativity than the other atoms, right? Think of high electronegativity as more willing to attract an electron, whereas less electronegative atoms are less willing to attract electrons, right? So for example, let's say we have this water molecule right here. This oxygen right here has more electronegativity than these hydrogens right here. So this oxygen here is going to pull in hydrogen's electrons, where we represent the pulling in of electrons by this arrow, right? This arrowhead is representing where the electrons are going towards. This tail is representing where the partial positive charge is going to be at. As this oxygen is gaining electrons, it's gaining negative charge because electrons are inherently negatively charged. As this hydrogen is losing its electrons, losing its negative charge, it's gaining a positive charge. So these hydrogens here are partial positive charges, right? So think of it like a tug of war of electrons. This bond right here represents electrons. the oxygen here is going to pull in those electrons more strongly because it has a higher electronegativity, right? It has a higher strength in pulling electrons compared to the hydrogen, right? So let's go move on to the octet rule, which are going to talk about the valence electrons. And the valence electrons are going to be the electrons in the outermost shell, right? So every atom besides hydrogen is going to want 8 electrons to be neutral to fulfill the octet rule, right? And they can do this in 2 ways. They can transfer electrons, or they can share electrons. Because let's say atom A right here has 2 electrons in the first energy level, and let's say it has 8 electrons in the second energy level, which is 4, right? 1, 2, 3, 4, 5, 6, 7, 8. And let's say in the third energy level, it has 1 valence electron, right? But now let's say atom B has 2 electrons in its first energy level and 7 electrons in the second energy level. Right? So the octet rule is saying that atoms prefer to have 8 electrons in its outermost shell to be full. Right? We see atom A is not fulfilling the octet rule right now because it only has 1 valence electron on the outermost shell. Whereas atom B has 7 valence electrons on the outermost shell, so it's missing 1 electron. Right? So to fulfill the octet rule, atom A is going to donate its 1 electron to that atom B right there. And as a result, we are going to have atom A with a full positive charge because it lost an electron. It fully donated this electron to atom B. And atom B right here is going to have a full negative charge because it gained a full electron from atom A. So that's the full transfer of electrons right there. So this would typically happen between metals and non-metals, right? The metals are going to be on the left side of the periodic table. The non-metals are going to happen to the right side, are going to be at the right side of the periodic table, right? So this atom here with the positive charge is considered a cation, whereas this atom here with the negative charge is considered an anion. So now let's look at the sharing of electrons now. So at the sharing of electrons, it's going to typically happen between 2 nonmetals. So let's say we have atom A and atom B with 2 energy levels. Its first energy shell is filled with 2 electrons, and let's say its second energy shell has 7 valence electrons. Right? Atom A is missing an octet rule because it only has 1, 2, 3, 4, 5, 6, 7 valence electrons, same as atom B. It has 1, 2, 3, 4, 5, 6, 7 valence electrons. In order for these atoms to have a full octet rule, we don't want to transfer electrons like that because if this atom A were to donate one of its electrons fully, atom B would gain a full octet rule, but atom A would have 6 valence electrons now, meaning that it's 2 away from the octet rule. So this is going to achieve the octet rule by sharing electrons and making a bond between atom A and atom B, right? And a bond is going to represent 2 electrons like that. So when we have those atoms share electrons, they are going to be bonded together now, right? Which is this bond that is formed between them, right? And that would fulfill the octet rule for both atoms, which makes them happy because they have a full valence shell, right? Full outermost shell, right? And we could draw that as this right here. This single bond between A and B that got formed has 2 electrons, right? 1, 2, 1 from each atom that are shared, right? So these are typically going to happen between non-metals, right? And when we go over the types of bonds, the transfer of electrons are going to be for ionic bonds. The sharing of electrons are going to be for covalent bonds, right? So let's go over that right now. Let's go over intramolecular forces versus intermolecular forces. Right. So some intramolecular forces are going to be ionic bonding, and the other one is going to be covalent bonding. Right. And ionic bonding is going to have a transfer of electrons, and they're going to form a lattice crystal from ionic units. Right. And they are typically from metals and non-metals. So an example of this would be NaCl, where Na has 1 valence electron and Cl has 7 valence electrons. This Na here can donate its 1 whole electron to chlorine to fulfill the octet rule, giving a full positive charge on sodium and a full negative charge on chlorine, right? And this is going to form a lattice shell where this is going to form a lattice crystal like that, right? And we call this table salt. But if we were to, let's say, put this into an aqueous solution with water, this lattice crystal is going to break. And I will explain why after we go over the intermolecular forces, right? So some intermolecular forces, actually, let's go over covalent bonding first. So covalent bonding is the sharing of electrons, but we have 2 types of covalent bonding, right? We can have a non-polar covalent bonding or a polar covalent bonding. So a non-polar is going to be an equal share of electrons, right? Where the difference in electronegativity is 0. And if that's the case, there's no partial charges. There's no partial positive charge. There's no partial negative charge. So this is going to be hydrophobic, right? There's no dipole moment. They are going to repel water. They dislike water. They are not going to dissolve in aqueous solution, right? Whereas a polar bond is going to have an unequal share of electrons where the difference in electronegativity is not 0, right? There is going to be a dipole moment where one atom is going to hog the electrons, which is the more electronegative atom, right? And that more electronegative atom, since it's hogging the electrons, is going to be partial negative charge. And the atom that is being ripped off of its electrons is going to be losing negative charge, therefore positively charged, right? So since there's dipole moments, this is going to be hydrophilic. They are going to like water. They are able to dissolve in water, right? So an example would be something like this. If I have propane and I look at this bond between carbon and carbon, they are the same atom, right? Carbon and carbon, so they have the same electronegativity. If I take the difference in electronegativity between them, it's going to be 0, right? So there's no dipole-dipole moment here, right? This is an equal sharing of electrons, making it a non-polar covalent bond. Whereas if I have water, we said that oxygen has a higher electronegativity than hydrogen, so it's going to create a permanent dipole moment between oxygen and hydrogen, giving this oxygen a permanent partial negative charge and hydrogen a permanent partial positive charge right there. Right. So now let's go over intermolecular forces. So there are 2 types of intermolecular forces that you can have. You could have hydrophobic intermolecular forces or hydrophilic intermolecular forces. And the hydrophobic intermolecular forces include the van der Waals forces, which is going to talk about size and dipole induced dipole forces, right? Where, for example, let's say we have this molecule, which has all non-polar bonds, right? Because this is a carbon atom, this is carbon atom, carbon atom, carbon atom, carbon atom. So the difference in electronegativity of these bonds are going to be 0, right? But these bonds here are still made up of electrons. And these electrons here are randomly moving around in the solution, in the environment, right? In the cloud, electron cloud, in their orbitals. And at some point in time, they are going to shift to one side over the other. So let's say randomly, the electrons are moving towards this side right here. That's going to give this carbon here a partial negative charge, and this carbon here a partial positive charge. So that will force these electrons to go that way, creating a partial negative charge here, because electrons or like charges repel each other, opposite charges attract, right? Positive charge is attracted to negative charge, but like charges repel each other. Positive charges repel positive charges, negative charges repel negative charges. So now this is going to attract another molecule where, let's say, its forces are going to be like that, creating a partial negative charge there, partial positive charge here, right? And that's the van der Waals forces, where it would increase as the size of the molecule increases, right? So if the size of the molecule increases, that molecule will have more van der Waals forces, which is a hydrophobic interaction, right? And induced dipole moment is going to be temporary charges, right? They are temporary because they are going to be fluctuating and transient. So those are the terms that you might see for this force, right? So those are the hydrophobic forces. The hydrophilic forces that you are going to see are going to be dipole-dipole, which is going to involve permanent dipoles, right? And this is going to be different than the intramolecular polar covalent bond, because intermolecular forces is going to talk about between molecules. So, for example, if I have this acetone here, this oxygen is more electronegative than the carbon, making this oxygen have a partial negative charge. And this carbon here have a partial positive charge. If I have another acetone floating around somewhere like this partial positive carbon here is going to be attracted to this partial negative oxygen, right? So the dipole-dipole intermolecular force I am talking about here is going to be between this partial negative oxygen and partial positive carbon like that, right? This is the intermolecular dipole-dipole force I am talking about, right? Not this polar covalent bond right here, because this is happening between molecules, which is a weak force, right? Because intermolecular forces are going to be way weaker than intramolecular forces. Intramolecular forces is like the direct transfer of electrons or the direct sharing of electrons, either nonpolar or polar. Whereas intermolecular forces are going to be between two different molecules, right? Where this is a dipole-dipole intermolecular force because the partial negative charge of one atom of a molecule is attracted to a partial positive charge of another atom of another molecule. The strongest type of intermolecular force that we will encounter are H bonds, right? And something would be considered H bonds if we have hydrogen attached to the three most electronegative atoms, FON, fluorine, oxygen, or nitrogen, right? So if I have water right here, where the partial charge of the hydrogen is positive and the partial charge of oxygen is negative, they are going to be attracted like this to other water molecules. The partial negative charge of the oxygen is going to be attracted to the partial positive charge of the hydrogen, right? And a lot of water molecules are going to surround itself in a way where the partial negative charge is going to be attracted to the partial positive charge, and like charges will repel each other, right? So that's different than polar covalent bond because the polar covalent bond here is the bond directly between the hydrogen and oxygen atom, whereas the H bond is happening between the water molecules, right? Where the partial positive charge attached to one of the three electronegative atoms is attracted to an electronegative atom, in this case, oxygen, right? So that's hydrogen bonding. Now let's go back to the ionic bonding. The ionic bonding is considered an intramolecular force in non-aqueous solution. Once we put it into an aqueous solution, however, that ionic bonding is easily broken, right? It's relatively strong in a non-aqueous solution, but once we put it into an aqueous solution, it's easily broken because into ions, like a chloride ion and a sodium ion, because the partial positive charged hydrogens here are going to solvate around the chloride ion, right? These are the partial positive hydrogen ions of the water, which are going to wrap around the chloride and take it away, solvate it, right? Creating a solvation shell. And this will dissolve the NaCl into ions, right? Where the partial negatively charged oxygens here are going to solvate around the sodium ion, right? These are the oxygens of the water that are solvating, wrapping around the sodium ion, creating a solvation shell there, right? And that dissolves the NaCl. Now, this is now considered an intermolecular force in an aqueous solution, right? Non-aqueous solution, intramolecular force. Aqueous solution, intermolecular force, right? Okay, so that's going to be talking about the differences between intramolecular force versus intermolecular force. Now, let's talk about the hybridization of atoms and the geometric shapes of molecules. So in this class, we're going to talk mainly about carbon, where carbon is going to either be sp3 hybridized, sp2 hybridized, or sp hybridized, right? So to tell whether a carbon is going to be sp3, sp2, or sp, we have to see how many bonding groups are attached to it, right? So a bonding group is going to be considered a single bond, a double bond, or a triple bond, or even a lone pair of electrons, right? So let's look at this carbon right here. This carbon right here has 4 bonding groups, 1, 2, 3, 4. And if it has 4 bonding groups, it's going to be sp3 hybridized, right? So I'm going to write the bonding groups in blue. So this carbon right here is sp3 hybridized. If we look at this carbon right here, it has 3 bonding groups, 1, 2, 3. And if a carbon has 3 bonding groups, it's going to be considered an sp2 hybridized molecule, right? Now, if we look at this carbon right here, this carbon has 2 bonding groups, 1, 2. So it will be sp hybridized, right? So a carbon with 2 bonding groups would be sp hybridized. So let's talk about the shapes of these molecules now. If a carbon atom is sp2 hybridized, it's going to have a tetrahedral shape, meaning that this carbon here is going to be like a tripod, right? Where it will have 2 flat bonds in plane with the iPad, right? 1 wedge bond, which means that that bond is going towards you, and 1 dash bond, which means that that bond is going away from you. And the bond angle between the bonds are going to be around 109.5 degrees. If a carbon is sp2 hybridized, it's going to be trigonal planar, right? So it's going to be in plane with the whiteboard or the iPad, right? And the bond angle between them is going to be 120 degrees, right? And it's going to be flat and planar, flat and planar. So some examples of this are going to be aromatic rings in amino acids such as tryptophan, phenylaniline, and tyrosine, right? These aromatic amino acids are flat and planar, sp2 hybridized, meaning that they could cross the blood-brain barrier and provide the brain with nutrients, right? Because some of these amino acids can be glucogenic, creating glucose for the brain and feed the cells in the brain, like astrocytes, microglia, from these flat amino acids that is able to cross the blood-brain barrier. Some sp3 carbons are going to be considered carbohydrates or sugars, and most amino acids, right? And these are not flat and planar. They have a tetrahedral shape to it, where they have a 3D geometrical shape to it, which cannot pass the blood-brain barrier and feed the brain, right? But these ones here are flat and aromatic because of the sp2 hybridization, which allows them to cross the blood-brain barrier and give the brain glucose or energy, right? So an sp carbon is going to be flat and planar as well, because the bond angle between them is going to be 180 degrees, making the shape linear, right? And it's also going to be flat, right? Now let's talk about the organic functional groups and resonance. So some organic functional groups that you need to recognize are going to be alcohol, phenol, amide, sulfhydryl, aka thiol, aldehyde, ketone, carboxylic acid, amine, ester, right? Where I'm going to draw out the shapes of these now. An alcohol is going to be when we have an OH group. This R right here is going to represent a random hydrocarbon chain. A phenol is going to be when we have a benzene ring attached to an alcohol. An amide is going to be when we have a carbonyl, which is a carbon number 1 oxygen, next to an amine, adjacent to an amine, which makes an overall structure of an amide. A sulfhydryl is going to be an SH attached to a random hydrocarbon chain. An aldehyde is going to be a carbonyl attached to a hydrogen. A way that you can remember this is that an aldehyde is a hydrogen hiding in the carbonyl, hiding next to the carbonyl. A ketone is going to be a carbonyl next to random hydrocarbon chains. You could think of it as like a key in the middle, right? Carboxylic acid is going to be a carbonyl adjacent to a hydroxy group, an alcohol, right? If that carbonyl was not there, this would be considered an alcohol. But because the carbonyl is here right next to the alcohol, adjacent to the alcohol, we consider that a carboxylic acid. An amine is going to be an R and so there's different types of amines, right? We can have ammonia, we can have a primary amine, we can have a secondary amine, or we can have a tertiary amine, right? Ammonia, meaning that nitrogen has no R groups. Primary amine, meaning that nitrogen has 1 R group. Secondary amine, meaning that nitrogen will have 2 R groups. And tertiary amine, meaning that nitrogen will have 3 R groups. An ester is going to be when we have a carbonyl next to an OR group, right? If that carbonyl was not there and we just have that OR group, we consider that as an ether. But because of the carbonyl that is next to or adjacent to that OR group, we consider that an ester, right? So let's talk about the significance of this in biochemistry, right? So alcohol is a polar functional group because this oxygen here is electronegative, more electronegative than the hydrogen and R group, making it have a dipole moment and therefore a polar functional group, right? So these alcohols here can react with carboxylic acids to form esters, right? Now, for the phenolic groups, you can consider that as aromatic alcohols. And because it's aromatic, it's going to be sp2 hybridized and flat, which is important because it could pass through the blood-brain barrier, right? So the amide is going to be polar because it has electronegative atoms pulling on that carbon, right? Making these partial charges here on these atoms, right? A sulfhydryl group is going to look like this SH group, where it's not going to be as polar as oxygen or nitrogen because it's not one of the big 3 electronegative atoms, fluorine, oxygen, or nitrogen, right? Where an aldehyde right here, you could think of that as the oxidized form of a primary alcohol, right? So this is a primary alcohol because this carbon here attached to the alcohol is attached to one other R group. We could partially oxidize this into an aldehyde, right? A ketone, however, is going to be the oxidized form of a secondary alcohol. Because when we oxidize the secondary alcohol, it's going to be oxidized into the ketone. Now, for the carboxylic acids, they are going to act as a Bronsted-Lowry acid that can release or donate a proton. Right, and that's going to be important for reactions and buffers. Amines are going to be considered Bronsted-Lowry bases that can accept protons. And they are going to accept protons by its pair of electrons on the nitrogen right there, right? Those are basic atoms because it can attack a proton using its pair of electrons. An ester is going to be found in a lot of biomolecules like lipids. It's going to be polar, right? Because it has these permanent partial charges here, right? Where the oxygen is more electronegative than the carbon, giving these oxygens partial negative charge and that carbon a partial positive charge, right? Okay, now let's talk about pairs of electrons, where the first pair of electrons that we are going to talk about is oxidation reduction reactions or redox reactions. So oxidation is going to talk about the loss of electrons, whereas reduction is going to be talking about the gain of electrons. So this might seem counterintuitive because reduction, you think of reduced, right? Because that's part of the name. So you think of losing something. But it's actually going to be the gain of electrons. So I like to think of it more directly by thinking of reduction as the loss of bonds to hydrogen, whereas oxidation is going to be the the loss of bonds to electronegative atoms, right? So reduction is going to be the loss of bonds to electronegative atoms, and oxidation is going to be the gain of bonds to electronegative atoms. Okay. Another way you could think about this is that reduction is going to be the gain of bonds to hydrogen, whereas oxidation is going to be the loss of bonds to hydrogen, right? So there's two different ways to remember this. You could use oral rig, where we could say oxidation, O, is the loss of electrons. Reduction is the gain of electrons. Another way that you can think about this is Leo the lion says grr. Right, but the most important thing here is Leo and grr, right? Because loss of electrons is oxidation, gain of electrons is reduction, right? So let's talk about this in terms of organic chemistry and biochemistry. I'm going to put the most oxidized state from left to right, and the most reduced state from right to left. Okay, so the most oxidized state is going to be the carbon dioxide, and then the carboxylic acid, and then the aldehyde, and then the alcohol, and then the alkane, right? This carbon dioxide here is the most oxidized state because it has the most bonds to oxygen. This alkane right here is the most reduced state because it has the least bond to oxygens and the most bonds to hydrogen, we could say, right? Where, let's look at this carbon right here. This carbon has 4 bonds to oxygen. Now let's look at the next one. This carbon right here has 3 bonds to oxygen, which is why it's less oxidized than that carbon dioxide right there. Another way we could say this is that this carboxylic acid right here is more reduced than the carbon dioxide, but the carboxylic acid is more oxidized than the aldehyde, right? And we could say that the aldehyde is going to be more oxidized than the alcohol, but less oxidized than the carboxylic acid, right? So it's like a relative thing when we talk about the oxidized and reduced state, right? So reduction is the gain of electrons, where we see that this carbon here has 0 bonds to hydrogen, so it's not reduced at all, right? This carbon here has no bonds to hydrogen, but it has only 3 bonds to oxygen. Whereas this aldehyde here has 1 bond to hydrogen. This alcohol here has 2 bonds to hydrogen. So this alcohol here is more reduced because it has more bonds to hydrogen. So that's another way you can think about that. Okay, so now let's talk about some examples of this redox reaction. An example is going to be when we have iron 2 plus that gets converted to iron 3 plus an electron. So this iron right here is losing an electron and gaining a +1 charge, right? So this is going to be oxidation. This iron here is going to be oxidized, right? So this is the oxidized state. This is the reduced state, right? Because oxidation is the loss of electrons, oil rig. We see that this iron here is losing electrons. So we are going to oxidize this iron, which becomes this oxidized state right here. Another example is going to be when we have copper 2 plus an electron and becoming copper 1 plus. This is going to be the oxidized state. This is going to be the reduced state, right? Because we are reducing the charge of this ion here, right? This ion here is gaining an electron, which is reduction. So the first reaction here is oxidation. The second reaction here is reduction. Okay, now let's talk about phosphorylation, dephosphorylation. When you see phosphorylation, think of adding a phosphate group. When you see dephosphorylation, think of removing a phosphate group, right? Add phosphate, dephosphorylation removes phosphate. And the enzyme that would do phosphorylation are kinases. The enzyme that would remove phosphate groups are phosphatases. And whenever you see a word that ends in ase, then that's going to be an enzyme, right? So an example is going to be ADP plus PI becoming ATP. We are phosphorylating the ADP. We're adding a phosphate group to ADP to convert it to ATP. Dephosphorylation is going to be when we have ATP and we convert it into ADP and inorganic phosphate, right? Where we are releasing a phosphate group, dephosphorylating, removing a phosphate group from ATP. And this usually couples with a reaction that gives it energy, right? Because we use ATP as a form of energy. And when we use it as a form of energy, we dephosphorylate it and convert it into ADP and the inorganic phosphate. ATP is adenosine triphosphate. It has 3 phosphate groups. ADP is adenosine diphosphate. It has 2 phosphate groups, where it lost an inorganic phosphate group right there. Right? Okay. Now let's talk about some acid-base reactions. Which are going to be deprotonation and protonation, right? Where a proton is going to be an H plus. That's different than a hydride, right? A hydride is going to be an H minus. So let's say we have an acid, HA. That acid is going to get deprotonated by dissociating into an H plus and A minus, right? So this is a proton right here. This is the conjugate base. This is the acid. And let's say we have some kind of base. This some kind of base is going to deprotonate the acid by attacking and grabbing that H and kicking out this A minus right here, giving us this conjugate acid and conjugate base, right? So if something gets deprotonated, something else has to get protonated, such as like if something gets reduced, something else has to get oxidized at the same time. If something gets phosphorylated, something else has to get dephosphorylated. So the base here is getting phosphorylated. I mean, the base here is getting protonated, and the acid here is getting deprotonated, right? Because this base here is getting protonated by this acid, and at the same time, because this acid is protonating the base, this acid here is getting deprotonated at the same time, forming a proton, conjugate base, and a conjugate acid. Okay, so let's look at some examples of this. If we have water and we react it with, let's say, HCl, water is going to be the base that's going to get protonated by the HCl, forming H3O plus conjugate acid and Cl minus conjugate base, right? The water here is getting protonated, the HCl here is getting deprotonated. Another example is going to be when we have, let's say, ammonia reacting with H2SO4. This ammonia here is going to get protonated by the H2SO4. And at the same time, the H2SO4 is going to get deprotonated. So we're going to form ammonium ion as a conjugate acid and HSO4 minus as a conjugate base, right? This ammonia is getting protonated. This H2SO4 is getting deprotonated at the same time. Okay, now let's move on to condensation reactions. So a condensation reaction is going to combine two molecules and release a water molecule, right? So an example is going to be forming a peptide bond between two amino acids. Formation of a peptide bond between two amino acids. So for example, let's say we have this amino acid, and we'll go over the general structure of amino acid later on. But for example, let's say we have this amino acid 1, and we have this amino acid 2. When we try to combine these amino acids together to form a protein, the primary structure of a protein, we're going to merge the carboxyl group of one amino acid to the amino group of another amino acid, right? So when we merge those two together and we try to make a new bond between the carbonyl-carbon of the carboxylic acid and the nitrogen right here, we're going to remove a water molecule, right? An H2O molecule. And this H2O molecule is going to come from a hydroxy group of the carboxylic acid and a hydrogen of the amino group, right? So when we make this reaction go through, water is going to be formed as a side product of this condensation reaction. And we are going to make a new bond between the carbonyl carbon of the carboxylic acid, which I'm going to label out in red. That's the new bond right there. New bond between the carbonyl carbon of the carboxylic acid and the nitrogen of the amino group of the other amino acid, right? Where the peptide bond right here is that new bond that got formed right there. And this functional group, like we said earlier, is going to be an amide. And this amide here has no free rotation, right? Because it can do resonance. This lone pair of electrons on this nitrogen right here can do resonance with the carbonyl nearby. And that resonance structure gives it a double bond character that is restricted, flat, right? Because single bonds have free rotation, they can rotate, whereas double bonds and triple bonds cannot rotate. This resonance characteristic of this amide group here is making this peptide bond unable to rotate. So another important fact to know about this is that single bonds are the longest, but the weakest, right? The longer the bond, the weaker the bond. Double bonds are shorter, but stronger. And then triple bonds are the shortest, but the strongest, right? So this has a bond order of 1.5 because it's in between a single bond and a double bond due to the resonance. So it's going to be, its bond length is going to be between a single bond and a double bond, right? A typical single bond and a double bond. So if its length is in between them, then that means its strength is also in between a single bond and double bond. But this will still be unable to rotate because it has some double bond character, right? This new peptide that we formed between these two amino acids, which if we string a lot of amino acids together by forming a lot of peptide bonds, that makes up the primary structure of the amino acid, okay? And there are a lot of other condensation reactions that we will look at in biochemistry, but let's look at the other types of reactions. Let's look at hydration versus dehydration. So hydration, think of water, hydrating, adding water, where let's say we have this alkene right here, and we react this with water, H2O. That's going to add the water molecule to this alkene, right? And add an H2O, right? And this H2O is going to be in this form right here, right? This H was not there before, this OH was not there before. So we're adding a water molecule, which could be split into a molecule. That's hydration. If we do dehydration, like let's say we have that molecule that we formed at the beginning, and we put it through H2SO4 acid and heat, that's going to dehydrate the alcohol and give us this as a result, right? Because we are getting rid of that H and OH to make a water side product. We are dehydrating this molecule here. So hydration is the addition of water. Dehydration is the elimination of water. Okay, so let's talk about the lipid phases. So a lipid bilayer is going to have a hydrophilic outer membrane and a hydrophobic inner membrane, right? So the inside is going to be hydrophobic and the outside is going to be hydrophilic. Let's say we have a sodium ion channel, right? And let's say we have sodium ions outside. And I'm going to represent the hydrophilic portions as a blue highlighter like that. And the hydrophobic section as a red highlighter like that. In order for this sodium ion to pass through the membrane, right? It doesn't want to pass through the hydrophobic region because hydrophilic, like the charges there, will be repelled by that hydrophobic portion right there. So that means that the sodium ion channel, the inner portion of it, the inner layer of it, has to be hydrophilic in order to allow for the passage of sodium ions through the membrane, the sodium ion channel membrane, like that. Right, so that's how they can pass through this lipid bilayer, lipid phase. And there's different types of transports that will have this similar phenomenon, which are like facilitated diffusion, facilitated transport, osmosis, or diffusion. Okay, so that's it for the Gen Chem and organic chemistry review. We are going to move on to the amino acid section now. Okay. Or actually, I will make the amino acids review video in a separate video, right? But this is the Gen Chem and organic chemistry review video, right? Where the lipid transport here, it could either be active or passive. And the types of passive transports are facilitated diffusion, facilitated transport, osmosis, and regular diffusion, right? If some hydrophilic polar molecule or ion wants to pass through the hydrophobic inner region of a lipid bilayer, it has to pass through a membrane where its inner portion, inner region, is hydrophilic, right? Allowing for the passage of hydrophilic or ionic species to pass through the membrane, the lipid bilayer, right? To pass through this hydrophobic region here. Yep. So I will see you in the next video, which we are going to go over amino acids, pKa, and pH for unit exam 1.